Okay, and welcome back to the lab. Tonight on the bench, we actually have a submission from a viewer. Somebody sent this into the channel. It's another Type 284. This one's got some damage to it. Kind of looks okay from the front, but we'll get into that here in a little bit. The request was troubleshooting a 284, getting deeper into it, and seeing what we can't do to bring this guy back. So let's take a look and see what happened to this particular 284, specifically if the tunnel diode is still good and if the other input is still good. So with that to say, I'm going to start working on cleaning it up, just get the top cleaned off a little bit. It's got this weird adhesive back film, kind of reminds me of the stuff we used to cover books in the 80s. It's like a weird mix between saran wrap and contact paper. It's awful. So I'm going to spend a little bit of time cleaning that off, but I don't need to bore you guys with that because that's just manual work. And then when I get into it, we will take a look and see what's wrong. This stuff was peeling off in little bitty chunks and was being really difficult to get off. Put a whole bunch of alcohol on the top of this, just out of the bottle. And that is actually counteracting the glue, and it's coming off in much bigger sheets now. So that was definitely helpful. One of the ways I get all the sticky stuff off of like the sticker residue and things like that off of some of the plug-ins is I use a lot of alcohol. There are places, if you have a lab and you want to go and you go through alcohol, the best way to buy it, you can get the MG Chemicals stuff, but you can buy it by the 5-gallon bucket. Don't buy it directly from MG Chemicals because they will need you to have a dangerous goods certification to ship it to you. Found that out the hard way, so I had to get one of those because it was an emergency. But Allied Electronics, DigiKey and Mauser stock them, but they don't stock... They stock the 1 gallon, but they don't stock the 5-gallon. Allied has been a reliable source of the 5-gallon buckets for me. I'm not affiliated with any of those companies. Just happens to be where I find supplies. Oh, the alcohol's drying. It's getting sticky again. Imagine that. A bit more. These squeeze bottles are nice, and they're not at the same time. They're nice because they hold a decent amount, but with a pressure change, they leak. So the pressure equalizes in the bottle. Air gets warm. It forces a little bit out the tip. You bump the bottle. A little bit comes out. So they're nice, but don't use bottle. I personally don't use bottles like that for anything other than distilled water and alcohol. I tried having a Menda bottle of acetone in the lab. That didn't go so well. It didn't stick around. So don't transfer acetone out of a standard, the container it comes in just evaporates from everything else I've tried to put it in. So I use acetone in the lab sparingly, but when I need it, I need it. This could be a lot worse. This could have sucked into this crinkle paint on the top of this and been an absolute disaster to get off. Also, in terms of isopropyl alcohol, I'm not too worried about getting it on my hands. Whenever I'm working with anything stiffer than that, I'll wear gloves. I am not too worried about isopropyl alcohol, only because it's the active ingredient in hand sanitizer. When I'm etching boards, ferrochloride, the liquid tin, those types of materials, oh yeah, gloves and safety glasses. If you guys are interested in those processes too, let me know. I'll see what I can... I haven't had to build many boards lately. And the one that I did need to build for the AA501, the features were too small to etch it in-house. So because it was a mini board and I needed plated through holes to get the size down, I sent that one out to a board house. And I am honestly not sure how long the camera has been rolling. I'm not sure how much my editor is going to cut out of this either. But I just spent a decent amount of time rambling about alcohol, so take that as it is. Oh, my hands are disgusting now. All the alcohol, or all the adhesive that was on the bottom of that sticky paper is now on my fingers. Also, since I'm talking about alcohol as a public service announcement for those who do not know, there is a great difference between ethyl alcohol and methyl alcohol. Methyl alcohol is toxic and poisonous. Do not drink it. Don't drink anything in a lab. That's always bad. Okay, a quick tech tip on buying alcohol, depending on what you guys are doing. I know a couple of my friends have some resin 3D printers, and they go through more of this stuff than I care to think about, cleaning up their prints and everything like that. These are the type of bottles that I usually use in a lab. These are both the same thing. This is just the 5-gallon pail. This is the 1-liter bottle. It also comes in a pump spray bottle and an aerosol can. I find the aerosol cans are good for cleaning out when I need a flushing action for a switch or something like that, giving these up. The aerosol cans are great. You can actually, on the aerosol cans, adjust the pressure by turning this high, medium, and low. Yeah, that's high, medium, and low. Rarely do I need high. High is pretty high pressure. Not sponsored by MG Chemicals. This is just the way I buy it. And there's not many purveyors of pure isopropyl alcohol. You can get it at the drugstore, things like that, but that's got water mixed into it. So the stuff you're getting at the drugstore is 70% to 90%. I do have some 70% in the lab. It's mixed with denatured water. I have one of these bottles, and then I have one of the spray bottles. I personally purchased the actual bottles because I liked the marking on them just to remind me what was in there. So I use those two. I use the spray bottle a lot and the 1-liter when I need to soak a rag or something. The spray can, obviously it's aerosolized. I have to buy these new. I can't refill these. So when these run out, they get recycled and I get new ones. To refill all my supplies of these Menda bottles, because this is what's in here. This can is the current going rate as today of 5/30 of 2021. So there's some stuff going on in the world which is affecting prices. The current going rate of the large jug is $181 US. The 1-liter bottle, which is this guy, is $14.66. I wanted to keep a couple of gallons around, and when I initially decided to start buying the large jugs, I wanted to keep a couple of gallons around, but I wasn't sure I wanted to go completely with a 5-gallon jug. But the way the pricing worked out was 3 gallons are sold as a block of 3. So if you buy a case, it's 3 1-gallon buckets. That is $135 for a case. The one pail is $181. So for $46 more, essentially the cost of a gallon, you get a free gallon of alcohol by buying the larger jug. Used to be a better deal than that, but prices are what they are. I can't change them. Used to be it was like $15 more. You got 2 extra gallons, so it made a lot of sense to buy the big pail. This is old. I've had this for a while. The real drawback of this pail is this port. This is a pretty big hole. So pouring this out and getting this into a smaller container is not the easiest thing to do. So to solve that problem, you get one of these, which is a drum pump. So there's a pumping action. You pull up on the top of this, and it'll actually pump fluid from down here out the nozzle. Now the important part on this, I got this one from easy action drum pumps. If anybody knows any other suppliers for these, I'd like to get 1 or 2 suppliers. As of right now, these are the only guys I know of that make these things. The important part is this coupler, and they make 1,000 different versions of these couplers to fit any barrel you have. So if you need a drum pump, you can get them in various sizes. The main difference in size is how long the pickup tube is, because it picks up from the bottom and pumps it out the top. But I had to call them and find out, because that pail does not have a standard size coupler, but they had them in stock. They were able to send them to me. The O-ring, this is a 2-piece coupler. Well, 3-piece coupler with the O-ring. The O-ring actually squishes between the top half and the bottom half of the coupler and locks onto the shaft of the pump, so it doesn't move when you're pumping it. But if you need lots of alcohol, the cheapest way I've found to buy it in large quantities is get one of those pails and a drum pump. I think when I bought this, it ended up running me about $23 for the drum pump. And then I just refill the smaller bottles. So when these run out, when these guys run out that you see in the lab all the time, I've been using the same bottles forever. I just keep refilling them. Can't do it with the aerosol, but I can do it with the liquid and spray, and then I refill this one out of here. So this goes in there. This gets a lot of use, and then the spray bottles and everything get refilled from the drum. Check your local listing, or check your local ordinances and local laws. 5 gallons of fuel is getting to the point where you may be running into some storage laws. Essentially, here in the U.S., it's illegal to store flammable substances in larger quantities than 5 gallons in some municipalities. That's why in our stores you'll only see a 5-gallon gas can, nothing bigger. It's because this stuff is flammable, it is fuel. Fire and this stuff doesn't mix. Definitely check your storage requirements. Some places I know you gotta store them outside. Some places have to store them inside or locked up in a cage, things like that. It all depends on how much you're storing and where you're storing it. Also, definitely do not leave the container open. It's alcohol, it evaporates, so you'll create a vapor hazard and a fire hazard. Don't do that. And the drum pump will seal it up nicely so it doesn't evaporate on you. That's how you can save a bit of money on cleaners. Well, let's take a look inside. When I get it out of the case, I'm going to wipe the top of this case off. This is still kind of sticky, so this needs to be done with some more solvent to get that glue off. But let's take a look at the back. Okay, the back, this piece will need to be removed again so I can get a plug on it. And, well, that looks a little strange. I don't know if the camera's picking that up very well. That's weird. All right, let's take a look inside. That came off pretty easy. Oh, it's kind of stuck. Okay. There we go. Oh, it's cleaner than the last one I looked at. That's always good. It's got the older golden board, but it is actually in incredibly good shape. There's not any corrosion on this. This looks real nice. Tunnel diode's disconnected, but no big deal. That cap will need to go. That'll need to go. It's an older one because it's got the carbon resistors in it. These are the power filter caps. These need to go and be updated to something modern. Snap caps will fit in there. If this one gets to that point where we do need to do something like that to it, I'm going to completely rebuild. We'll put in bigger power filtering caps just so it even gets a cleaner supply. So that looks good. On the front of it, everything looks okay. I'll have to clean it. We have a pretty recent serial number. Yeah, we're over 100,000. So B101558. This came out a little too easy. So that wasn't holding it on very well. But let me get another one so I can kind of show you the damage. Okay, here's the other one that was in the previous video. This one we know has the bad tunnel diode in it. I do have some TDs on order from Russia. They are currently in transit. I don't know exactly why I don't know exactly where they are in transit, but they're on the way. So, waiting on the mail, as with everything. Yeah, so there's a difference. That got punched. Now I'm looking at this, and that's a decently thick piece of aluminum. Like, that's a really nicely thick piece of aluminum on there. So that's got some strength to it. And what amazes me is this thing has been hit with enough force to bend this, to cave this piece of aluminum in a good inch from where it should be straight. Because it should be straight like this. So this is caved in a half an inch. Something hit this with a considerable amount of force. The only thing I could think of that would hit this hard enough to do that much damage and not leave a mark in this area on the back is if it got dropped on the plug. If this took a hit with the plug sticking out, here, and it fell like that could force the plug up and cave this in. That's the only thing I could think of that would do that kind of damage and not just completely gouge out the aluminum. Yeah. Just, jeez. All right. Well, let's see if we can get this to the point where. Well, let's check the tunnel diode first. So the enclosure's disconnected, which is fine. I'll figure out what the wire colors are from my other one that we know works. This one's actually connected up correctly, so I can match the color scheme on that. I need good storage for my tiny tools. I got good big tool storage. I need small tool storage. However, very tiny adjustable wrench. It is the perfect size to get right in there and grab the nut that is right here that holds the enclosure into the front of the frame. Now, why is this particular wrench so important? Because of the thickness. It's thin enough to get in there. A larger adjustable wrench just cannot get in there and get that to be removed. I don't exactly know what size bolt that is, but all my spanners that are that big are too wide to get in there. Once the nut gets loose, the tunnel diode enclosure will slide backwards. It'll also start to spin, and it just pops out. And not on the connector, but on the back side of the enclosure, you just pop it up, push this forward, and the whole thing slides and lifts out. And there's our airline. So, how do we pop the airline apart? Flat spots here. You can do this with a larger adjustable wrench. I just found this one works well. Actually, I do it from the back side because of the way the enclosure goes together. It's easier on the tunnel diode. So you push together like so, and then you... Okay, this one's going to need some persuasion to come apart, maybe. Yeah, I need something a little bit bigger. Okay, just broke the nut there. You want to hold this enclosure, because what you don't want to have happen is the tunnel diode, which is right here, spinning on the airline. So you want to hold the enclosure and back this off with a hand, and then go straight up. There is the important part. Back one didn't want to come apart either. A good rule of thumb is to unsolder this connection before you take the enclosure apart. That keeps, if this turns when you're loosening it up, that keeps that resistor network from spinning and twisting in there. That resistor network is one of the important pieces. That outer resistor is unobtainium. If that breaks, you will need a donor for a new one. Actually, that looks really clean. Wow. I don't see much corrosion in there. That looks clean. Let's get that resistor network out of there. Okay, let's check and see if the resistor is good. For those who haven't seen the previous 284 video, this is the back termination resistor. There is two carbon composition resistors inside here. This should read about 600 ohms, 660 ohms on the front end. This resistor right here should read about 700 ohms on the front end. That's what sets up the bias for the tunnel diode. So this is the positive side of the tunnel diode, which is resting up against that plate right there. There's the TD in its enclosure. This is the negative side of the tunnel diode at the back end of the airline. We have a back termination resistor of 54.4 ohms because it's a 50 ohm terminator at 5 gigahertz. And then we have, this should read about 660 ohms of resistance for the internal resistors. But every single one that I've taken apart, I'm now working on my third, every single one of these has been over 700 ohms. So let's see if this one follows the same pattern. If it is, we'll have to rebuild this resistor. Not a huge deal. Took me a while to find parts for it, but at the end of the day, I found out a 1206 surface mount resistor will actually fit inside the termination resistor. So we can use modern surface mount parts to rebuild this resistor. You have to be really careful when you do this with the termination resistor because this is unobtainium. If this gets messed up or melted or anything like that, you're in a bad day. There's not much you can do about it. But these two carbon comp resistors, we got a solution for that. For those of you who haven't seen how the 208 works, this is kind of incredible that it actually works the way it does. You have, this sits in the enclosure, and you have a positive voltage up here and a negative voltage coming. You have a negative voltage coming down the spring-loaded airline in the back. So what happens is you have a negative voltage coming in, square wave, negative 15 volts, a positive 15 volt square wave coming in at the same time. So you have a voltage differential of about 30 volts. So you're slamming it with negative 15 from the back, positive 15 from the front, and then you slam it from the sides with the tripper pulse, and that kicks the tunnel diode up over its IP. So it just goes, meh. And that quick jump over IP is what causes the incredibly fast edge square wave that comes out of the front of this, but it's also at a very low voltage. It's at, 200 millivolts? Yeah, 200 millivolts. But it's got less than a 70 picosecond rising edge, which is the same thing as saying it's a 5 gigahertz pulse, which is kind of incredible considering it's coming out of this tiny diode. When you pull the TD out, it's a good time to check that resistor in there. This should be about 700 ohms. I'll pull up a spec sheet and figure out exactly what it should be. This should read about 660 ohms, and these are pretty precise resistors, so they shouldn't drift too much. Like I said, this has always been out of spec. So let's take a look at the back termination here real quick. And our survey says 54.4, so the back terminator is good. Our other survey says 711. So we know what's wrong there. We'll be rebuilding this if the tunnel diode's good. We still have to check that. So I'm going to pull the tunnel diode out of here. There's a plastic frame. Actually, let me get my tweezers. Those are a little big. My surface mount tweezers are a little too flexible for that, but these duckbill tweezers are good for pulling these guys out of here. So we'll just get in here and gently, do not grab the diode. Always manipulate the TD width on the plastic enclosure. Trippers are a little close, so I have some of them that'll just slip right out. Some of them you gotta just pop this connector loose. Do not use pliers on the connector. Make sure you grab the outside edge. You do not want to grab this barrel. Very important. Actually, loosen up the other one while we're here. I'm sorry if I drift off a frame. I'm paying attention to what I'm doing so we don't mess up the enclosure. Okay. And there's a bit of magic. That little guy right there is $285 if he's blown up. That doesn't look right. Our resistor should be straight up and down, but its leg goes off to the left, coming down into the enclosure. So that's weird. Let me check and see if I get a good mating. Yeah, the connector's the right way. Okay, so it didn't rotate in the housing. So, tunnel diodes and ohm meters. Do not test a tunnel diode with an ohm meter. You can't do it, they don't work. The reason it don't work is tunnel diodes conduct in both directions, so the ohm meter will tell you it's good in both directions. However, that is a good indicator of if a tunnel diode is good or not. If you do get the same conduction in both directions, that can be a clue as to that the TD is good. It's better than if it's blown open and can't read at all, which is what happened to my other one. But to truly test a tunnel diode, let's get a curve tracer. All right, because these tunnel diodes are so expensive and so rare, I'm going to verify all my settings before we move forward. Curve tracer settings as set on a 577, 6.5 volts. Series resistor, 120. Actually, I'm going to back that down to 500. Polarity is plus, not plus DC, but plus, because we want the sweep. Vertical sensitivity is 100 millivolts per division. Oh, I'm sorry. Horizontal sensitivity is 100 millivolts per division. Vertical sensitivity is 2 milliamps per division. Now this is a 20 milliamp tunnel diode, so it should kick over when we get close to the top. Because on this particular curve tracer, it's the 10 division one, so it would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So it should kick right close to the top. Maybe not exactly at the top. Now, tunnel diodes, because they conduct in both directions, polarity is incredibly important. So, I'm going to take you through double checking the polarity here real quick. I'm going to print out the schematic. Actually, I think that's on the tech wiki for the chamber. So let me grab that real quick, and then I'll be back, and I'll show you how I'm setting up the curve tracer. On the curve tracer, collector is positive, emitter is ground. That's why we have the red lead on collector. The base, or the, not the base, the ground lead on emitter, which is good. Those come out to this is just test leads. Those come out to banana jacks. What I have found for these tunnel diodes, because they are so incredibly fragile, don't take it out of the plastic enclosure to test it. Test it in the plastic enclosure. But you guys have seen these in a lot of my videos. I really like these pin grabbers. They're small. They grab just hard enough to maintain a connection, but they don't grab too hard to rip something out. So I really like these little pin grabbers for testing scopes and things like that, power supplies and everything. So This setup is a, what is this? Oh, it's a Probe Master setup. This is the 9000 series leads. They're segmented like this. You can buy a whole bunch of different ends. Sometimes, especially when I'm testing power rails and amplifiers and stuff like that, because I have the meter bank up top, I can hook up 6 different meters to all the power supply rails, flip the amp on, and go, yep, all my power rails are there. Okay, here's our schematic of what's in the simplified airline. Here's our 750 ohm resistor in the front. Here's our 2 resistors inside of the 3 resistor network. It's a 390 and a 270. So, yeah, right at about 600, 660 is where they should be. 710, they're out of spec, they need to be replaced. I still have to measure this guy, I haven't measured it yet, but here's our 21 milliamp diode, D180. And positive to negative is the way the current flows. Just to check that to make absolutely sure. Positive anode through to the cathode, anode to cathode, and there we go. So positive to negative. Everybody may think I'm going a little overboard making sure the polarity on this diode's right, but because tunnel diodes will conduct in both directions, if you wire them up backwards, they will conduct until they explode. Well, not explode, but burn up. So, yeah, I don't want to burn it up. It's an expensive diode, and they're incredibly rare, and there's really not a good replacement for them. So, in the meantime, let's measure the resistance real quick while the curve tracer warms up. I've got 741 to the side of the barrel. So, 750, that resistor's in spec. For whatever reason, I don't know if it's thermal or what, because they're inside the network, I don't seem to find much drift here. These are always off. I don't know why. Tunnel diode. One easy way to tell the polarity of the tunnel diode, because it's always in question. There's a cutout in the plastic housing where the metal of the diode actually touches the conductor. Now you can see, sorry, I'm inspecting the diode because this is impossible. This is set up wrong. It can't not be set up wrong. I have a sneaking suspicion this diode's in there backwards. Now, that's a pretty bold claim, given that I just took this apart. However, it's very hard to see, but as the diode comes down into the enclosure, there is a strip of plastic right here at the bottom that insulates. Let's see if I can zoom in on this. I don't know if the camera will focus. So let me get a pointer here real quick. Right here at the very bottom of the enclosure, there's a hole that the conductor goes through, where plastic covers the conductor at this point to insulate it from the positive side of the pulsar. This cutout in the pulsar is to accommodate the resistor on top of the enclosure. Because what ultimately happens is the positive pulse comes in on that side, the negative pulse comes in on the back side, but they have to be separated by the plastic by the plastic enclosure that's in here. They have to be separated. So I am pretty sure the way this is wired is impossible to do, because the front side of the TD, which would be facing the negative airline, is wired so that the back side of the contact is touching the top of, or is touching the front of the enclosure. So because you have a lead of the tunnel diode touching the positive side of the enclosure, you're shorting both sides of the pulsar So the way this is constructed, here we go. It's super zoomed in, sorry. The way this is constructed is this pin right here is shorting the airline. Focus, come on. Focus, there we go. So this pin is touching the back, and the front of the tunnel diode is touching the front. Or no. Yes. Front or back, either way. But this pin and this side of the diode are shorted together, but they're shorting both sides of the pulsar together. This can't work. There's no way this worked. So let's see. I'm not going to give it a lot of current, but let's see if we have what looks to be a functioning diode. Okay, this is looking good. I have the diode hooked up the way I believe it to be polarity-wise. So that's 2, 4, 6, 8 milliamps. 10. I'm only going to get it close to 20. Much more over 20 and we'll burn it up. 12. Not enough current. 10. Or 2, 4, 6, 8, 10, 12. 14, 16, 18, 'kay, that didn't go. There it goes. That is a functioning tunnel diode. It needs a little bit more current. However, yes, the polarity is backwards, but it didn't burn up. I did check it in the reverse direction. What I noticed on the curve tracer in the reverse direction was the line was straight up and down steep. That's what you should expect of a tunnel diode. The tunnel diode will be a resistor in the reverse direction, and it will be a tunnel diode in the forward direction. So now that I know it works and now I know the polarity is right, I'm going to bring it up slowly again so you guys can see what happens with the tunnel diode. But this D180 is good. It's just in backwards. So we're climbing. There's I now have the scale set at 5 milliamps per division. So because this one's actually a little higher than before. So there's 5, 10, 15. You can kind of see how the trace is curving. If I back it down, you'll kind of see this curve come in. Right there, how it's curving. That is what a tunnel diode should be doing. And then IP is right about there. That's what a tunnel diode should do. Now, I don't want to go any more than that because I don't want to burn up the tunnel diode. But you have IP, and then it's snapping over here. So this is a confirmed good tunnel diode. I will go through that in depth. I have a printout of when I tested the other tunnel diode I had in the Type 284. So I took some pictures of that so I can talk about that in depth without torturing this tunnel diode because this is a bit of unobtainium. The way I had that hooked up, positive was on this side, negative was on this side. So this tunnel diode never worked. If somebody hasn't done this through time, and this is the way it's shipped from the factory, this tunnel diode never worked. This is impossible for it to have worked because of the way the enclosure's made. So what I gotta do, I actually need to flip the tunnel diode around. Carefuling. Yeah, it's dotted on both sides. There's not a good way to... Oh, yeah, there's the dot. Okay. Now I have to find out if TDs are dotted on the... I lost it. Yeah, I don't know. I lost it. Okay, the tech manual says dot on top lead. So, let's put that in the top lead facing me. There's the dot. It's on the top lead. Oh, this is tedious. Okay, let's check for polarity. Make sure we have it right. Since we now know this TD is good, we can just double check polarity real fast, and then we should be able to... Nope, I'm going to get even a smaller set of test leads. These aren't even grabbing it at this point. I have a smaller set of pin leads, which I'm going to use. Here are my even smaller set of leads. So, here's what we do. So the notch for the resistor is positive, which means my negative is coming out the bottom over here. So here's negative. Here's positive out the front end. See if that's in there right. Now it just flipped over. That's in there right. We can already tell because of the curve. There's the tunnel diode action. Perfect. Okay, so every repair is different. I was not expecting that. I was not expecting a backwards tunnel diode. As you can see, the tunnel diode is now, the positive side of the tunnel diode is now up against the top of the resistor. And I did do that. I put it in backwards again. It's the correct polarity now. The problem is the tunnel diode is flipped. So I need to pull it out, flip it over, and put it back in. Okay, that is now correct. So what you need is the negative side of the tunnel diode, which connects to the back of the airline, has to go through the insulating ring on the plastic, and it folds forward. Actually, they both fold forward. They both fold towards the rear of the enclosure. The positive side, this face, the positive face of the tunnel diode has to be up against the positive pin along with the rest of this lead. So it was in backwards and it was flipped over, so that's why it wasn't working. The way the enclosure is built, it can only go in one way. It only works one way. If this isn't right, there's no way it works. It shorts things, it does funny things. And the tolerances you're working with is you're literally working with the thickness of a diode. Because those two, this part of the airline and that part of the airline mash the diode. So if my tweezers are the diode, those two parts of the airlines squish the diode like this, and it's just suspended between those two pieces of metal. That's how it gets all its contact. So I was not expecting that when I started this repair. I was not expecting a diode that was jacked up. I will be sending an email to the person that sent me this tonight, so they'll know what's going on before I post the video. But yeah, no, that one was entertaining. That right there is a correctly assembled tunnel diode. Now, you're actually looking at the back, because here's the notch in the resistor. That goes over the resistor in the enclosure, so it can mate with the front of the barrel, and then the back of the airline mates with the back of the diode. Here's the enclosure. I will not be able to do this on camera, at least with these tweezers. Let me get the other tweezers, see if I can get this on camera, just so you guys can see what this looks like. Alright, here's our tunnel diode. Here's our enclosure. And I'll use the bigger tweezers to push it home into place. That's what it should look like. Alright, there we go. So, battle number 1 of getting a 284 working. Yeah. Half of it's done. Now all we gotta do is the airline. Okay, since I already went into great detail on repairing this resistor in the other video, I'm just gonna go ahead and do it. This video is already getting kind of long. At least I feel like I've been talking for a while. So I'm going to just get this one fixed, and then bring you guys back when I have to reassemble the airline. And welcome to Curves of the Weird World of Tunnel Diodes. I haven't fixed the resistor yet. I'll do that here in a minute. But this is how I knew the tunnel diode was good on my other 287. I tested it exactly the same way, the curve tracer. Since I snapped a picture and the tunnel diode's out of the picture, I'll just kind of go through it. So the way the curve on a tunnel diode goes is current rises till it hits IP, then it snaps back down to here, and then it rises again until it runs out. But this is where I stopped the curve tracer. If I had kept turning up the current, this line would have just kept rising off the screen. So what happens is the curve tracer sweeps. As it starts the sweep, voltage starts rising, and so does the current. Current rises, current rises, current rises, current rises, hits IP, snaps down here. Current rises, current rises, current rises, current rises, and continues to rise until the sweep comes back. And then when it comes back, so what happens is, comes up, snaps down, comes up, snaps back, comes back down, up, and it does that. So very odd curves for diodes. You can see these ghost lines. These are the retrace lines. That's how fast it's switching. The beam's just jumping. You can see a little bit of the retrace here. You see a little bit of the retrace here where it starts slowing down. But it doesn't do this. It actually does this when it comes back. So very oddball, very oddball diodes. But you can get some really fast edges out of them, and they're good to go. So this one's good, which means that 287 or 284 is at least working towards being salvageable. So let's look at repairing the back. What I think I'm going to do is I'm going to take the back off of the crusty 284 and put it on the nicer 284, and then work on reassembly. But first, I got to get this resistor swapped out and get that fixed. Okay, I've got the back disconnected. What I'm really hoping I can do is I'm hoping I can pull this off, turn this sideways, and push this in. That'll let me remove the back plate of the unit without disconnecting any of the wiring. The plug already fell out internally because it just sits here. There was screw here, here. Same thing on the bottom. Whole plate comes off. This is held in by 2 bolts that are underneath the cover. So you pull the cover off, and then it exposes these 2 bolts. You pull those off, and then this pops out. So what I'm really hoping is we can do that right there. And there's our mangled piece of back plate. And yeah, it's there's no hits, there's no scratches, there's no impacts. It's just bent. So, out with the old and in with the new. Okay, you can actually see the just extreme angle that this is borked at. So I'll see if I can get that straight, and we'll throw it back on the other one just so it's a complete unit. It did bend right on the weak spot. That's where the most metal's removed aside from the top, but So it did bend right at the weakest point in the back frame, but that's still a stout piece of aluminum. I don't think I can bend that back with my hands. I'll need some bigger tools. Here's what the back end looks like. I'll get the back plate put back on. Next stop is the bulk filters. They need to be replaced. So we'll get into that once I get everything reassembled. I didn't notice this until I started putting the back on and the bolts weren't lining up. If you look here, the entire frame is racked and pushed forward about an inch. So I actually gotta move everything backwards so it lines up with the back frame again. This thing took a really good hit. While we were in there, I got the main filter swapped out. These old Sprogs, 1250 at 50 volts. I had some 4700 at 50 volts. They're snap caps. And some of the difference 50 years makes, or 30 years makes, and that's a 1200 50 microfarad. That's a 4700 microfarad cap. It's even smaller. So I had to wrap some electrical tape around the barrel of these caps to get them to hold up. They're hiding back in here now. New filters, lots more room in there. I'm going to hook up some power supplies. I got the power bank on. I'm going to hook them up to the filters just to make sure we're not exceeding the 50 volts. Old vintage capacitors are much more tolerant of overvoltage than modern capacitors. Modern capacitors are not tolerant of overvoltage at all. So if you're working on tube gear, doing things like that, working on things with some soft supplies that bounce around for a little bit, always overvolt the capacitors. Doesn't hurt them, but undervolting them and then the power supply spikes to, if you put a 450 volt capacitor in something with tubes, power supply spikes to 600 volts before the tubes come in. That'll burn the cap up. So you got to have the cap rated for the highest voltage it's going to see, but running it at a lower voltage won't hurt it. So let me get the bench cleared off a little bit, get some power set up. I think we're ready to plug this thing in and at least see if there's signs of life. No smoke. Okay, I set the hoppy off to the side, so we'll see we're feeding at 119 volts, but at no current draw. This is the hoppy's plugged into the isolated ground and current limited supply. I have 3 of the bulbs switched in, which gives me about 1.5 amps before the bulbs clamp. So let's go ahead and turn this on and see if we at least have signs of life and no smoke. Oh wait, I need to hook up the meter real quick. Hang on. Okay, I have not started this up yet, so you guys are seeing this for the first time. I have the meters up here, which I have connected to the plus minus supplies. There's 2 caps. They're wired backwards, so the minus there's a positive supply and a minus supply. The caps are wired appropriately for the supplies. So I'm going to go ahead and flip the on button and let's see what happens. 37 volts on the capacitors. That's good. About a 0.5 amp current draw. That's good. 118 volts. That's okay. We have no lights on the current limited supply, so that's good too. And it looks good. Looks like the caps are holding at about 41 volts and 38 volts. So that is a plus. Let's hook up the sine wave generator to a scope and see if we have signs of life out of it. We didn't get any major sparks and no smoke, so that is positive number 1. All right, I've got the scope plugged into the 7854. We're going to try it on a 10 nanosecond sine wave. I'm using the 7A19. All right. I got to speed this up, but hang on a second. Let me move you guys over to the scope. Well, I can't complain about that. So there's the 10 nanosecond sine wave. Let's try the 100 nanosecond square wave. Nope. 1 microsecond square wave is a nope. 10 microsecond square waves are a nope. So, we have a problem with the square wave, for sure. I bet you that's indicative of what our problem may be. That's actually on the top side of the board. So I'll have to spend some time with the schematic. I'll reseat some of the components, things like that, see if we can't find anything. Something very easily could have been jostled by the damage. I'm also going to clean the switch and a few other things, make sure we get good contact on the switches. Alright, let's try 1 nanosecond sine waves. We do have some 1 nanosecond sine waves. I am pushing this frame to its absolute limits with the 1 nanosecond sine wave, so doesn't necessarily shock me that it's struggling to display the waveform, because 1 nanosecond is way too fast for a 7A19 and a 7854. So definitely could be the 1 nanosecond may be working. I just can't validate that at the current time with my lab. But cool. So let's check out the square wave generator, see what's going on with it, see if we can't get it working. But the power supply is healthy, not drawing excessive current. Everything looks like it's going pretty good. Yeah, something sick in the square wave. All right, more troubleshooting. But we have progress. So we have a half rebuilt tunnel diode enclosure and a at least functioning power supply. So progress. As with doing the easy stuff first and having unknown hardware, a bit of switch cleaning. So I'm working on cleaning out the square wave amplitude switch, because we did have a little bit of square wave, but it wasn't quite right, and this looks like it's a resistive divider switch. One thing I also noticed is the square wave switch was loose. It's moving around in there. So I got to tighten that up, get that fixed, and then continue cleaning the switches. It's also starting to rub on the face of the unit. So gonna get the switch dressed and then see what's next. Okay, let's use the 7854 to take a look. All right, so we'll go to scope and a time base. So after cleaning, we have a decent square wave, but let's get some parameters of it, see if we're in the ballpark. So we'll go to ground. We'll hit ground to tell the scope where ground is. Come up to DC, and then we'll capture it with 10 averages. Go to stored, and let's see, our peak-to-peak voltage is, ground. You got to tell ground after you store it. Peak-to-peak, 800.5 millivolts peak-to-peak. So I have it set to 1 volt peak-to-peak, so it's a little bit light. So I think what I'm going to do is I think I'm going to pull out all the transistors, just because the impact this thing took, and just reseat everything that's socketed. See if that does it. And then we are going to have to calibrate it, obviously. This thing is way out. So, but what do we got for period? We should have about 10, I have it set to 10 microsecond square waves. So we'll hit period. That's not right. Okay, that's the scope being dumb. All right, let's set this to AC. We'll bring ground to the center. AC couple this. And actually, center will hit ground there. So we will AC couple this, capture with 10 averages. Go to the stored waveform. And then let's do a period search. There we go. Okay. when you're hitting ground, you're essentially giving it the 0 level. That's telling it where to actually take the reading. So when it's DC and ground's down here, the computer in the 7854 is very rudimentary. So AC couple it, because when I hit, if I go back to scope, if I hit ground, it's telling it this is the reference. And what it does is when you say this is ground reference, that's also where it takes all the measurements off of. So it's taking all the measurements off the center line. So if I go back to AC, and we go back to stored, we have a 10.6 microsecond period, which we're on 10 microseconds, so we're good. So our timing's right, but our amplitude's a little light. Let's check 1 microsecond. So we'll go to scope. It sped up. There we go. Turn this up a little bit so you guys can see. Very cool. So we'll acquire that. Done. Now we will set our ground point. Done. And we will go back to stored view. And we will do a peak-to-peak measurement. Yeah, we're actually right at the same amplitude, so 805.4. So the amplitude looks like it's just a little light, but it did change frequency. So let's take a look at the period. These should be 1 microsecond square waves. Period. Ground reference it. Period. You have to ground reference before every measurement. 1.009 microsecond periods. So yeah, it looks like our timing's right, but our amplitude's off. So is that a calibration issue? I'm sure it is. I'm sure you do calibrate the amplitude on this. I'm not 100% sure what happened. Also, the amplitude, one of the amplitude pots got smashed into the front end of this thing when the impact happened. So the fact that it's off doesn't shock me at all. And I did notice one other thing in the unit that is curious, and I'm going to have to look at the service manual to figure out what's going on with it. But we have our square waves back. We have our sine waves back. Now all I have to do is see if we can get our tunnel diode back. And if we can get our tunnel diode back, that's cool. We'll have another functioning 284. I will need to get faster gear for the lab. So these 284s, they're actually pushing the lab past its limits. The frequency limits of the lab at the moment in the time domain are the 7A19 and my 7904A, which is a 500 megahertz frame. This is a 400 megahertz frame, so the 7A19 is plenty home in here. These 7A26s are real nice because they're dual channel and they're 1 megohm input, but they are only good to 200 megahertz. So the way you get the faster in these frames is you go to the 7A19 or the 7A29. They also make some dual channel versions of those. The problem is, which it's not really a problem, but it's something to be aware of. This is 1 megohm input, which is what most people are used to on their scopes and things like that. This can take a scope probe. To get faster, especially in this time period, you had to go to 50 ohms. So the 7A19, the 7A26, the dual 400 megahertz plug-in, they make one of these that's 400 megahertz, but if you look real close, it's not 1 megohm inputs, it's 50 ohm. So you got to be on, you're at 50 ohm when you go faster. So the fastest 200 megahertz plug-in, anything more than that, you're in 50 ohm. You need 50 ohm probes, and you need to stay in the 50 ohm architecture. Do not hook a transmitter up to the front end of this and say, I'm going to read the power of my 50 ohm antenna. You will blow the front end of this apart. That's actually what happens to a lot of these is people who are unaware of the input limits. Scope, go in, transmitter, and go by plug-in. You blow the fuses, you burn out the input. These are sensitive inputs. Yeah, it's a 2 watt max input. So anything more than 2 watts and it's done. One of the things I'm gonna video that I'm going to have coming up in the lab. I'm not sure the order that these are going to post. This one might post after that one. I have some stuff coming with some very sensitive 50 ohm inputs. So that will be the huge updates for the lab, and everything's good. One's already here. The other one's shipping, and I just need the shipping company to treat it gently, hopefully. So awesome. So we got our square wave back. We have our everything back. I'm caught in Chipmageddon, so I have to wait for resistors to ship in. I have a wheel of the 390 ohm resistors. I don't have any 270. 270s are back ordered for over a year. So I did order a small quantity of 270s. They should be here soon. So I'll be able to continue working on this and see if I can't get this up and running. But as of right now, everything is looking pretty promising that this one's going to come back. So we know we have a good tunnel diode. I need a good terminator resistor. We'll sanity check the outputs of the inputs to the air line before we hook everything back up and just make sure everything there looks all right, and then we should be good to go. But that is working awesome. Okay, after getting the two bulk board decoupling caps replaced, I beefed up their capacitance. They were 100s by 25s. They're now 220s by 35s. There's one right here and one right there. This is the positive test point. This is the negative supply test point. They're both reference chassis ground. So I've got them all hooked up. They should be 20 volts. So I'm going to move you guys up to the meters. The DM502s are just my sanity check meters. When I do when I actually get into doing the calibration and getting everything more precise, I will definitely move over to the 65 or the 7510. Okay, you guys are at the meters of interest. This is my negative supply. This is my positive supply. I'm going to hit the power button. Boom, 20 volts. Negative 20 plus 20. So at least to the limits of those meters, they are set to go. Board should be happy. We'll need better stuff to check it further. Still waiting on the resistors to ship in. They should be here shortly. But we will get on with it when they get here. Okay, so some parts came in to rebuild. This is just a heatsink chunk that I had laying around. Give me a nice platform to solder on without burning my bench. I need to rebuild these resistors, and I need a 390 and a 270 ohm. I had a wheel of 390 ohm from the last 284 that I did, so I ordered a wheel of 270 at the same time. I'm still waiting on that wheel to come in. Fortunately, I was able to order 10, so I have the resistors I need to continue, but parts supplies are what they are. So let's get into it. I'm going to get these soldered up, and then I'll bring you guys back when I'm putting the resistor together. Okay, here is the assembly done. I measured it. It's 659 ohms, which is right where it should be. This is the old resistor network that I pulled out. Okay, here's the side with the solder that I'm going to need to fix. I ran some deoxit around the ring over here, so got the corrosion all cleaned up on that, so that looks good. So what I need to do now is I need to get that resistor network internal into this resistor. So I'm going to use this vise for that, and I'll show you how I do that. Okay, here's the resistor network I reassembled. Measuring from here to here, I get 658 ohms, which is expected. Measuring from here to the back termination, I get 54 ohms, which is expected. So this resistor network is now back in spec. To get the surface mount diodes to solder, this cap had to be removed. It was in the back of the resistor. So what I did was I just desoldered that and then pulled pulled it off, pushed the surface mount resistors right up there, and then filled that whole area in with solder so it looks like that. So that is good there. So now I have to reassemble the airline, get everything all put back together, and then we'll give it a test. I sanity checked the 284, and I was getting, it was a little light on one of the amplitudes, but I was getting good pulses. Nothing was completely bonkers when it came to, it's not like I was getting 30 volts on one of the rails or anything like that. So everything looks good for me to hook up the tunnel diode again, and let's see if we get some pulses out of it. Oh, and to give you guys a size of scale, that's the size of a Q-tip. So this stuff is really small. Okay, I have everything hooked up. I'm ready to turn the pulser on for the first time. See if this rebuild was all worth it. So, I'm going to move you guys over to the scope. I've got the 7603 fired up. Nothing special. Just looking to confirm function at this point. I actually need faster gear in the lab to fully calibrate one of these. So if it's working, that'll be a stop point until I either get a sampling. What I need is I either need a sampling plug-in for a 7000 series, or I just need to get a 6 gigahertz modern scope. So haven't decided which way I'm going to go yet. Yeah, I don't know. So, but in this case, let's take a look and see what we got. Okay, we are at the scope. We'll turn up some intensity. I'll turn the readout on so you guys can see what the settings are. So it's 50 millivolts. So if the pulser is working correctly, we should get about a 200 millivolt pulse. So at 50 millivolts, that'll be 4 divisions. 500 nano. Probably good to start. Obviously, this thing's pretty fast. So flip this on. And the moment of truth, going to flip it over into tunnel diode mode. Okay, so we don't have any step response, but we do get some action out of it. Let me try to adjust the bias. Let me just adjust the bias of the tunnel diode here real quick. There it is. There's the step. So it was just a little light. I had to adjust R133 just to give the tunnel diode just a touch more bias. So that there's the step response. I don't know what else to say, except that's fantastic. See if I can get the delay trigger die. There it goes. Stretch it out a little bit. So yeah, there's our step response. I'm ecstatic with that. So 50 millivolts per division, 51, 50. So it's a little high, but that needs to be this needs a full calibration given everything we've done to it at this point. So I do not have the gear to do a calibration at this point, but we were able to bring this one back to life. Fantastic. While we're here, let's just check the other side. 1 nanosecond sine waves is going to be way too fast for this plug-in, so, but there we go. That is actually too fast. Oh, there it goes. There we go. Zoom in. There's 5 nanoseconds per division, so that's 10 nanosecond square wave, so that's working. Yeah, 1 it can't pick up at all. So let's see, 100 nanoseconds, 1 volt square wave. Nope. Oh, there we go. That's 1 mic. And 10 mic. So there we go. And there's 100 nano. So the square waves are working. 100 millivolts. There we go. 10 millivolts. There we go. It's working. The switch is just a little dirty, so I need a little bit more cleaning on the switch, but other than that, it's good to go. That's just an intermittent on the switch. Thanks for stopping by the lab today and taking a look at the repair of this Type 284. I cleaned the switches up, and that took care of the intermittent issue, so it was just a switch contact issue. So this guy's needing a calibration, but the repair itself is done, so he's back up and running. This is still the old one that was mine. This is the one with the blown out tunnel diode in it. I have some Russian tunnel diodes on order. They are not here yet. The last time I checked the tracking number, they are in the US, but they are stuck in customs, so no idea when they're going to get here, but we'll go from there. So thanks again to the viewer who sent this 284 in. This was a challenge. This was fun. The plate that was bent, I have straightened it and put it on the old unit. So this guy actually still has a chance of being resurrected, even though parts were stolen off of it. He still just needs a case. Or I have a case for it. He just needs a tunnel diode, and then we'll go from there. Yeah, thanks again for stopping by, and I will see you guys in the next video. This was fun.